Hi and welcome back to another LeetCode video. Today we're looking at LeetCode 3186, maximum total damage with spellcasting. It's a medium problem and it's a one-dimensional dynamic programming problem. And you will find that it's actually quite straightforward to solve if you know a little bit about one-dimensional dynamic programming questions. So without further ado, let's just get into it. A magician has various spells. You are given an array power, where each element represents the damage of a spell. Multiple spells can have the same damage value. It is a known fact that if a magician decides to cast a spell with damage of power at index I, they cannot cast any spell with damage of power at index I minus 2 up until power at index I plus 2. Each spell can be cast only once. Return the maximum possible total damage that a magician can cast. And in terms of constraints, so it's guaranteed that we're at least going to get one spell, and all spells have a positive power value. Right, so let's look at an example here. Example 1. So input array is the power, so each entry in this array is a spell. And you can see here that spell at position 0 and at position 1, they have the same power. And the rule was that if we pick index I as our spell to cast, then we cannot cast the spells that have a power value between minus 2 and plus 2 of whatever the power value was of the spell that we just cast. And yeah, so here, if we cast a spell with power value 1, that means we cannot cast spells with 0 and negative values. Well, they don't exist anyways. But we can also not cast spells that have value 2 or 3. So 3 is going to be out. And the only other spell we can cast if we choose cast a spell with power 1 is the one with 4. And that would mean the total power of the spells that we cast is, well, you might think it's 5, but actually, if you look at the spells that we cannot cast, it doesn't say that we cannot cast another spell of the same power. So actually, we can cast first two spells because they have both the same power value. We can cast them both, which gives us a sum of 2, and then we can cast the spell with the power value 4. So it's really important to understand that here, they're not talking about the indices in the power array. They're talking about the actual values in the power array, which gives this problem a nice little twist. Now, in the second example, here what we can do, well, we can cast the spell 7, but that means we cannot cast any spell that has the value 6 or 5 or 8 or 9. So we could only cast 7 and 1. That would be 8 combined. Or we could choose to pick both of these power equals 6 spells, which would already be 12. And the spell with power 1 is far enough from 6. Means we can also cast it, so the total would be 13. Right. So how do we implement this? Well, we need, obviously, when we want to, well, there are two different approaches. So one would be to remember, which powers are basically forbidden after we cast a spell. So we don't cast any of the spells that have these power values, minus 1, minus 2, plus 1, plus 2. Or we could sort the entire array of powers, which allows us then to iterate through this array linearly. And we would just skip over indices where the power of the spell is within the range that needs to be excluded. So I think that is the more efficient approach because it uses less space. And you can see here the length of the array of spells is 10 to the 5th power, which is quite long. And that would all be, in the worst case, a space they would have to use. So maybe just sorting this whole thing in n log n time is better because we'll have less messing with memory operations, etc. So that's what I would do. However, in order to be able to sort this, we we can't just, well, we could actually just sort it, but we can make that a little bit easier for us. We could compact that a little bit. If we could compress these spells with counting sort, for example, because the information, if we want to maximize the total damage, it is clear that if we cast a spell with a certain power, we're going to cast all of the spells that have the same power value immediately to maximize the possible total damage. So what if we had the information that if we cast a spell of power 1, we immediately increase our damage dealt by the power value 1 times how many spells there are with that value. So as a first step, I would use a counting sort to build up essentially a new array that contains each power value once, but also the total damage that we deal when we pick that value. So I'll just create a damage hash map to begin with. This is just for the counting sort. And you can use, you could use a counter object from Python. I like to do it by foot, so I'm just going to implement this for power in our power array. If the power value is not in our damage array hash set, then we're just going to edit. Power is equal to 0. And in any case, we're going to increase the damage value for that power value by plus equal power value. So now we have a hash set. That's not going to help us to iterate over it later. So we'll turn this into an array that we will sort then. So we will just iterate over the power and the damage dealt for power and damage dealt in damage items. Right, so we're now iterating over the keys and values inside this hash set. And we are writing it into an array, which we're now going to sort. Damage to sort. So this is already an O of n log n operation, time and O of n space, right? Excuse me. And yeah. And so the next step is, well, we now have something that we can use to iterate over, as we've discussed. And when we iterate over this array, let's say we have index 0, index 1, index 2, index 4. Now, we have the choice of picking the spell at index 0, right? And if we were to assume that, these are actually the spell values, if these are the spell values, that would mean we could not pick this spell and we could not pick that spell. Similarly, if we didn't pick the first spell, but the second, we cannot pick the third and the fourth. And same way, if we start from the third index, or the third power value, we couldn't pick the 2 ones before or the 2 ones after. Okay, cool. Right. So, well, we need a little. I'm going to do this in a recursive way. I'm going to need a little helper function, and the only thing that we need to pass to that helper function is an index that tells us where in our damage array we are currently, and then from there, from index I, we're going to pick the damage at that index, the next index, and the one after. So we will simulate, picking the next index, the one after, and the one after that. However, we need to make sure that we skip indices where the damage values are too close to the damage value at position I in our. So let's deal with the base case first. if I is larger or equal than the length of damage, well, then the damage is going to be 0. That we will do. Now, however, if so now we need to well, fast forward the index. If the damage value at the current index is smaller or equal to the one that we currently have. So our damage array contains power and a damage, right? So we're going to extract that from the array for our index I. And we need to do that to be able to compare it. So okay, that's how we get the power value of the spell at position I, and how many spells we have with that power value multiplied with the power value. That's our damage. Now we're going to forward our index while I is smaller, length of damage, right? And well, we want to make sure that the power value at position I, well, as long as the power value at position I is smaller or equal than the power value that we just pulled out, plus 2, which is this constraint here, because we are traversing the array from the left to right. As long as that is the case, we're going to just advance I by 1 position. So that's essentially the skipping over of the next two indices and the power values with an increment of 1. Okay, so now that means we can actually pick the next spell at position I, right? So we moved out of this range that doesn't allow us to pick the next, pick the spell. And yeah, now we just, what we do is we're going to return maximum value between choosing for the next spell, the one that follows immediately after our range ended that we could choose. But, you know, we could also, well, we can decide to pick the next value or the one after or that one after, right? So that is what we need to do now in our recursive call. We need to explicitly jump over the index at I and the index at 1, so that we make sure that we explore all of the options, all of the spells that we can take from that position. So this is basically just exploiting the overlapping subproblem. And then we add to that the damage value that we have in position I before we increase. And that is pretty much it. Now, when we start calling function, we have to do the same thing here. Consider all of the possible starting positions, like we have to start at the first index, at the second, or the third. Because if we start at the first index, we cannot pick the second or third, which is exactly why we have these other options. Pick spell from. Right, so this is everything we need to solve this problem. Now, in order to avoid computing the same helper function multiple times, we're going to use cache, a memory. And I'm just going to use the cache annotator here, at cache annotation Python, which makes sure that we store the return value of the helper function when it's called with the parameter I. So that because every time we go into the recursive call, we have a branching factor of 3, which means that many of the path or the previously computed helpers of I will be recomputed unless we cache the result of previous computations. All right, so now let's run the tests. They pass. Submit this. Right, and so that passes. And well, does anything here change our space and time complexity? No, of course not. I iterates over all of the indices that we have in the damage array. They are in the worst case the same number that we have in our power array. The worst case is when the power array has all values that are distinct, so no two spells have the same value. In this case, the damage array has exactly the same size. And yeah, so then that would be an O of n base complexity to store all these results. And because we're also not storing any of the, well, we're not recomputing results, and we're iterating through the array in basically from left to right, it also means that this entire process also takes only O of n time spent inside our helper function. Might have a branching factor, but that's also an O of 1 operation if the value is already cached. So I guess that concludes this problem. Yeah. I wonder if there's another way to solve this without the counting sort in the beginning. There probably is. Then you would just have to iterate in your while loop and check, whenever. Probably have to check, if I guess P is the same as damage at the index, then you would add that to your damage value. Right, so then actually, yeah, why not? We should probably try this. So we sort these damage values. But actually, if you do that, then our +1 +2 doesn't really work anymore, does it? Because it might be that we have the same power value here. So that would means we would have to like return the last pick, the last power value that we picked, use that as a criteria to iterate over indices that we cannot pick, etc. So yeah, that would be possible to do, but it's a little bit too involved for me to do now. So that completes that